My name is Bryson and this is a documentation of my 2025 summer project. As with all engineering students, I wanted to take on the coolest project topics I could think of, rockets. So after getting inspiration from many other engineers on YouTube who have worked with rockets before, I decided I would dedicate the summer towards developing my own single-use rocket motor. My initial requirements were simple: make a cheap, dispensable, short-range rocket engine able to be remote detonated. And here's how that turned out. To create the propellant, I used a mixture of 65% potassium nitrate, 35% sugar, which according to my research yields the best results. However, due to limited materials, I could only work with the less effective form of potassium nitrate. Now the one I need is potassium nitrate. This one has nitrogen and soluble potash, K2O. Unsure with how this new compound is going to react as a propellant, there's only one way to find out.
Oh, watch out!
Reaction.
So clearly the potash worked, but we just had to try it out again.
It's burning black.
Yeah, door closed.
A very satisfying result that my stump remover could be used as a propellant. Just want to take a moment to say that I'm aware of the dangers that come with handling and manufacturing such reactive compounds, but rest assured, everyone in this video are trained professionals and are equipped with the proper PPE. Our 65-35 compound mixture worked best under high temperatures and high pressures.
Oh! Yo!
Yeah. Prototyping phase has started. Right now I'm just doing the rocket tip, just to see if everything fits. Seems to be printing swell. The next day, I modeled some rocket tips and fins in SolidWorks to specifically fit my PVC pipe design and 3D printed some prototypes. I wanted these rockets to be light and cheap as possible, so I started off with some pretty basic designs. Update, I got these heads printed. Very, very fine work. All last night, so I got all that, and then I have these. I'm sort of just frying in the sun to glue together. Wonderful, wonderful. They all fit so freaking well. The day, June 18th. We're going hardcore on this. Here's my PPE, and then here's the.
I'm literally making chlorine gas. And this guy's gonna be like 5 feet away, so...
Yeah, sure. Proceeding with the same propellant recipe that was tested on day 1, R&D spent most of day 3 making more propellant, with some new members who provided the whole team with the necessary PPE to uphold safety standards.
You're trying to mix from the stump the KNO3?
Yeah, the KNO3, the sugar, and hydrogen peroxide.
Also, it's not really KNO3, it's some other bullshit. Or a K20, I don't know what it is.
K2O. Welcome to the Chemistry's R&D department of Santos Lab. I'm a research assistant, and Bryson Santos is the principal investigator.
Yeah.
65-35, we have K2O, and also sugar.
We do?
Yes, I added it.
Yes, you added it.
Get away from that, bro.
Oh my god.
The propellant continued to provide good results, so we experimented with just how a little bit would react in one of my rocket prototypes.
I think it just needs a higher, like, a higher, there it is.
Órale.
It produced a much bigger reaction because of a higher pressure environment, however it also made a lot of smoke and wasn't enough to fully propel the rocket. Okay, today is... Oh, sorry. I got injured. July 7, Monday, about day 4 maybe of testing.
Okay, so how do I test this?
How do you what?
So how do you want me to test this?
Just put it into this bowl and then we'll figure it out. For even better results, we decided to change the recipe a bit to maximize combustion. I ordered some proper KNO3 online and added a few grams of iron oxide powder, which makes the mixture a red color. Now, have some pure Gordons.
Can you get something to pack it in?
Iron oxide also acts as an oxidizer similar to the KNO3 and should help with the propellant reactivity.
Wait, do I need a mask on like this?
When it starts boiling in.
That's easy.
Hey, I found a new ramp.
I don't know, cut.
warped it.
That's a lot of
warped
progress
it.
compared to before.
True. Yes.
What's up? Today is August 2.
August 2nd.
We're finally out here in the range. We're gonna light some jaunts up.
Which rocket number is this?
As you can see, this is a sand pit. Now this test session did not go to plan. Either it was because there was too much wind that day, or my lighter didn't have enough heat, but the propellant would not ignite enough for combustion. I also speculate it had to do something with the propellant. The sugar could have been overcooked, causing it to lose its reactive properties, or it could have collected too much humidity to properly ignite. So instead, I tested our remote detonation device. Indeed. Very high tech.
Incredibly. All right.
There we go, watch this.
Ready? Fire.
It's worked. Okay, not that good. But also,
It's turned black.
okay, but the match went off, as you can see.
This is true.
Just gets snuffed out.
Could it be with the fuel?
It has to be with the fuel. Oh, like burning. I was gonna make a warhead. It is day, I don't even know what, 6, day 7. Oops. Let's stop. As you've seen from the last couple of videos, the test did not go as planned. It's quite disappointed. You see the, they even have the stand right here. So I went online, I looked at, some example model rockets of specifically Richard Naka, his amateur rocketry website, but he also used rockets out of PVC, similar to what I did. I'm basing my rocket entirely off his. Few key differences. The PVC I used before was 1/2, beefing it up to 3/4, and I'm getting the sorbitol. Mixing up the propellant. The sugar is just so hard to deal with, bruh. I'll be making cement. I'll be putting it in here. That's gonna make like a little nozzle and I'll shoot it up. So basically I got to work on following Richard Naka's own PVC rocket tutorial by first creating a nozzle out of cement inside the pipe. He uses these handmade tools to make a mold for the cement, which I 3D printed myself. It actually went out really well. I mean, not came out really well, but it went. The process wasn't that crazy. But yeah, once I get this this process down, should be good. "30 minutes ago, I made the final batch. This is like the final batch of the summer. It's September 15th. And I move in September 21st. So this is now or never. Just want to quickly explain here that this propellant was molded into grains instead of being poured directly into the rocket. After the grains dried, I put 4 solid grains into each rocket. Yeah, I have, that's the last 2. So I have 8 total. All these are filled with fuel. 8 total rockets. I'm gonna test one. I'm just gonna do a static test and only on this improper cast. To use is going to be magnesium ribbon. There we go. first ever static testing. That was huge. These are big motors.
As you can tell, I was clearly pleased with how the rocket performed. There were some inconsistencies when it came to combustion, and further tests are needed to fully understand the rocket's capabilities, but these are promising results that reinforced I was headed toward the right direction.
Welcome back. Today is June 17, 2026. Yes, 2026. It's been a year since I started this, but we're back. We're going to be testing the rockets that we just made earlier using this thrust stand. I didn't record the process of making the thrust stand. I didn't think it was that important, plus the video would be too long, but you could check it out. We're using an Arduino Mega on an LCD screen. Using a code and a load cell, I made my own thrust stand, which calculates the force that the rocket makes and sends all the data over here. Now we'll see at the end of the video how good the data results are. And over here we have our test subjects that you've seen me painstakingly make. We have exactly 6 of them. We'll probably test only about 2. And yeah, that's the preface of today's experiment. Okay, so yellow light means it's
They're just bullets. It's awesome.
connected to that. It's connected. We're going to protect this. First test, first static test of the year.
Step a little bit further back.
Let's chill.
Okay, so post-test analysis, it was pretty good. Nothing blew up. The apparatus just stayed there. Look, as you can see, there's a lot of deformation. It was really inconsistent, which is not good, but these propellant grains have been chilling here for at least like a year, so I'm not expecting the best performance. I see like little spurts. I'm not sure if it'll actually take flight, but at the end, it was pretty consistent.
Now that we have valuable data from yesterday's static test, it's time to analyze the data in post-processing. Graphing the force over time recorded by the thrust stand, you can see how consistent the results were with how the rocket stuttered in combustion, giving the peak shown on the graph. The rocket was able to produce a maximum force of 1,043.6 grams with an average force of 220 grams over 19.762 seconds burn time. Using this data and given the rocket parameters, we can simulate from this test how it performed in actual flight. From this graph, we can find the total impulse delivered by the rocket by integrating the force curve over time. Since this curve is extremely complex, I used the traps function in MATLAB to find the area under the force curve, which gave us a total impulse of 45.31 Newton-seconds. Because we are simulating flight, aerodynamic forces like drag come into play. Because the rocket is shaped like a cylinder with a diameter of 0.0254 meters, credible online sources estimate the coefficient of drag to be 0.75. Since the drag equation is 1/2 rho v squared times drag coefficient times the cross-section area, we have a drag force equation. Finally, we can't forget about gravity, whose force actually changes with time due to the fuel being burned over time. For simplicity, assume a constant burn rate of propellant mass starting at 0.0625 kilograms of propellant at the start and 0 kilograms at the end, giving us a mass change over time of the m dot equal to 0.1625 minus 0.003166 times t. Now that all these forces are accounted for, I compiled all these factors into MATLAB and plotted them onto a graph showing the altitude and velocity of the rocket trajectory. Miraculously, this rocket will manage to take flight and reach a peak altitude of 1,321.8 meters, or 4,336.6 feet, with a maximum speed of 116.8 meters per second, or Mach 0.34. This rocket data analysis marks the end of what I wanted to accomplish from this project, which is to successfully synthesize my own rocket propellant and build a rocket engine prototype. With the vast availability of the engine chassis materials of PVC and cement, and the amount of power density packed into the propellant, I consider this engine to be cheap, disposable, and well-ranged with the thrust stand data predicting its flight capabilities of up to 4,300 feet. This is one of the biggest projects I've taken upon, and I'm glad to have learned so much about what being an engineer is like through the problems and setbacks I faced along this nearly year-long journey. I'm also incredibly grateful for all my friends who helped me in this project. I learned how powerful collaboration with others in various fields is when managing a multidisciplinary project such as this. Be on the lookout for even bigger projects in the future.